In Chapter 7, we're looking at chemical reactions. Before we discuss our lecture today, let us quickly review what we covered last lecture, which was basically the first part of Chapter 7. We looked at the rates of chemical reactions, which means, is a reaction very fast or is a reaction very slow? In chemistry, we use the term kinetics to represent the rates or describe the rates of reaction. So that's the chemical term that's used to describe rates of reactions. We also looked at factors that affect the rates of reactions. We looked at molecular collisions. We pointed out that molecules will have to collide. Reactant molecules must collide, and there must be effective collisions with the proper orientation for a reaction to occur. We also discussed activation energy, which means that the collisions between molecules, reactant molecules, there must be sufficient energy generated so that the reactant molecules can go on to form products. That energy, that minimum energy, is called the energy of activation, or the activation energy. We also looked at concentration of reactants. We pointed out that if you have two reactants or a reactant going to product, and if you should increase the concentration of one of the reactant, the rate of that reaction will be increased. Typically, if you double the concentration of one reactant, the overall rate of that particular reaction will be doubled. We looked at the effect of temperature on the rates of a reaction. As you can imagine, increasing the temperature causes more molecular collisions, and hence the reaction rate will be faster. And of course, the typical observation is if you increase the temperature by 10 degrees, the reaction rate will be doubled. We also looked at the presence of a catalyst. A catalyst is a substance that's used in a reaction but not consumed, basically to increase the rate of a reaction. The rate is increased because the reaction finds an easier route to go to the product. This easier route requires less energy, so the energy of activation is less, making it a faster reaction in going from reactant to product. Let us look at what we'll cover in today's lecture. Today we'll look at chemical equilibrium or equilibria. We'll look at more than one. And reversible reaction. So we'll make that definition and we'll look at some examples. Then we'll look at equilibrium constants. So instead of looking at the rate constants as we did for the first part of this chapter, we will look at equilibrium constants. So we will define equilibrium constant and we will also do some calculations. So make sure you have your calculators ready so we can calculate equilibrium constants and make comparisons. Next, we look at the factors that affect a system that's at equilibrium. A French chemist, Le Chatelier, made these observations and known as Le Chatelier's principle. So if a system is at equilibrium, if there's a change in concentration of the reactants or the products, will that affect the equilibrium? If there's a change in temperature of a reaction that's at equilibrium, will that affect the equilibrium? And lastly, if there is a change in pressure of a reaction that's at equilibrium, will that affect the position of the equilibrium? But we'll get into each of these in more details. Let us first look at reversible reactions. So let's make sure we understand this concept of reversible reactions, and then we'll look at equilibrium. So let's look at this reaction, for example. If we mix carbon monoxide and H2O, here it is, carbon monoxide in the gaseous phase and H2O in the gaseous phase, a reaction occurs. It will produce carbon dioxide and hydrogen. So this is the reactant, or these are the reactants here, and here are the products. It so happens that if you get carbon dioxide and hydrogen, mix them together, you will get carbon monoxide and water. So now these are the reactants. Notice they were the products before. But now if you mix these two, you get these as the product, and notice that these were the reactants before. So what happens? If you mix these two reactant here as shown down here, mix CO2 and H2, this reaction, you will get carbon monoxide and water. And to represent that, we use this representation here. Notice it's two arrows with a single head on each arrow, a single barb on each arrow. This end is for the forward direction, so it indicates that this is going in this direction to produce carbon monoxide and water from CO2 and hydrogen. We know that if carbon monoxide and water are mixed, it produces carbon dioxide and hydrogen. So the reverse reaction can occur, and this represents the reverse reaction. So this reaction here is a representation of a reversible reaction using this symbol as the representation of reversible reaction. This symbol right here at the bottom. So let us conclude what we've learned from this. So an equilibrium here is called a dynamic equilibrium. Why? Because if you mix carbon dioxide and hydrogen, after some time, you will get carbon monoxide and water. And after some time, the concentration of carbon dioxide, the concentration of hydrogen, the concentration of carbon monoxide and water will be constant. It will be constant. So if you had that reaction and you carried it out and you came back the next day, the concentration of all four will be the same. It so happens that it's dynamic because the reaction is constantly going forward and constantly going backwards. So but they equal. The rate of the forward reaction and the rate of the reverse reaction are the same, so that the concentrations of each of the reactant and each of the product remains the same. That's called a dynamic state of equilibrium, as opposed to a static where it gets there and that particular molecule does not change. So, summary. At equilibrium, there's no change in concentration of either the reactant or the product. No change. No change. And the reaction, however, is still taking place. The reactants are still being converted to products, still being converted in a forward direction, and the products are still being converted to reactants in the reverse direction, and that's why it's called a dynamic equilibrium. So make sure you understand these terms, and make sure you understand what a reaction at equilibrium means. Let's make a comparison and see if we can determine a constant to measure the relative concentrations. And this is done here by determining what is an equilibrium constant. So what we're doing here is we will determine an equilibrium constant for a particular reaction, which will reflect the concentrations at equilibrium, the concentrations of reactants and products at equilibrium. So as you can imagine, each reaction will now have a different equilibrium constant specific to that reaction. So let's look at how we determine equilibrium constants. So let's look here at reactant A reacting with reactant B to produce product C and also product D. As you know, we all have to work with balanced equations. So these letters here, the italics letters here, represents the coefficients for the balanced equation of the stoichiometry. The coefficients. So it has been defined that the equilibrium constant here is equal to concentration of C, product, in square brackets. The square brackets here just means the units will be concentration, raised to the power of that coefficient. The other product molecule, D, its concentration raised to the power of the coefficient for the balanced equation. And that's all divided by the product of the reactant molecule A raised to the coefficient A and the concentration of reactant B raised to the coefficient B. So that's the definition of an equilibrium constant for a particular reaction. That's called the equilibrium expression. So that's something that you'll have to, well, not memorize, but make sure you have it on your cheat sheet whenever you take a quiz or a test, because it is an expression that's known in chemistry for calculating equilibrium constants. The important aspect, though, is can you apply this to solving a problem? So let's see. So if we write this, if we have this equation here, or this reaction, notice that this symbol represents it's at equilibrium, it's reversible, and at equilibrium. The question now is, can you write an equilibrium expression to show what K is for this reaction? So we know that from the previous slide, it's the products raised to the appropriate coefficient divided by the reactant raised to the appropriate coefficient for this balanced equation. So here we go. CO2 is a product, and here it is. And notice it's raised to 1. Typically 1 is not written because it's understood, because the coefficient here is 1. Hydrogen is a product, here it is, and notice the coefficient here is 1. And so this is 1, but it's typically not written. The reactant, carbon monoxide, here it is, it's 1 and raised to 1 and not written. Water is the other reactant, and notice it's 1 because of the balanced equation, and it's raised to 1. So if you were asked to write the equilibrium expression for this reaction here, it would be this. Okay, let's take it further. Here's another reaction. Here's a reaction here. Notice that the coefficients are different in this case. For the reactant, it's 1 for hydrogen, it's 1 for iodine, and it is 2 for HI, the product. So the equilibrium expression is right here. So the equilibrium expression for this reaction is HI raised to the power 2 squared. So you'll have to use your calculators here whenever we do a calculation. And of course, hydrogen is a reactant, it's at the bottom, and iodine is a reactant, it's at the bottom, and raised to 1. So that's the equilibrium expression. What's given here are the equilibrium concentration. So I2 is 0.42 moles per liter. That's this one. H2 is 0.025 moles per liter. That's this one, per liter. And of course, HI, the product here, the concentration at equilibrium is 0.06 mole per liter. So the question now becomes, what is the value of equilibrium constant for this reaction given these equilibrium concentrations? All you have to do is to plug these numbers here into this equation and solve it using your calculators. So here we go. So once we put these numbers in, this is what you should get. Important here is that this number is squared because of the coefficient from the balanced equation. And of course, these numbers are raised to 1, which means that it's just the plain number. You punch these numbers into your calculator. Make sure that you square this number here and divide here, and you should get 55. So again, you may want to pause the video here and make sure you do this calculation on your calculator and make sure you get 55. So this is the answer for that equilibrium for the previous reaction. Let us look here at a comparison between equilibrium and rates, just to tie this all together. So for the reaction shown here that we've seen before, carbon dioxide, hydrogen to give carbon monoxide and water. Let's make some observation here. The rate of this reaction has no relationship to the equilibrium constant. Let's see why. So you mix reactants here. So just imagine at time 0, you mix carbon dioxide and hydrogen. At time 0, we have no products. But after some time, we will start getting products. That's the rate, the time to get the first molecule of product. The time required for that to happen is reflected in the reaction rate. And of course, as you know, that depends on the activation barrier, etc. It has nothing to do with the equilibrium constant, because the equilibrium constant deals with the reaction after it has reached equilibrium. After it has reached equilibrium. Thus, it's possible to have a large K. A large K means that we have lots of products. The concentration of the product molecules are pretty large compared to the concentration of the reactant. So once again, a reaction with a very large K means that the concentration of the products at equilibrium are very large compared to the concentration of the reactant. That's a large K. If there's a small k, that means that the concentration of the reactant molecules at equilibrium are much larger compared to the product molecules. Another way of looking at this, if the equilibrium constant is small, the concentration of the product molecules are small compared to the reactant molecules, which means that that's a small k. So you should be able to look at two k values, equilibrium constant, and predict which should have more reactant molecules at equilibrium or which would have more product molecules at equilibrium. Okay, let us look here at Le Chatelier's principle. As we mentioned, Le Chatelier was a French chemist, and he made quite a few observations about a reaction at equilibrium. So let us start our discussion by looking at this reaction here at equilibrium, measured by this equilibrium constant, or represented by this equilibrium constant. Okay, so if this reaction here is at equilibrium, so in other words, we mix carbon dioxide and hydrogen and let it sit for some time, not measure the rate, just have it sit until it reaches equilibrium. We have a fixed concentration of carbon dioxide, a fixed concentration of hydrogen, a fixed concentration of carbon monoxide, and a fixed concentration of water at equilibrium. Those will be the equilibrium concentrations. What Le Chatelier observed is that if we add more reactants, so you go ahead after a couple of days and you add more carbon dioxide, will that affect the equilibrium? Will it shift it to the right or shift it to the left? Will this number be any larger or any smaller? We'll discuss that. If you remove the reactants, instead of adding, you remove reactant, take it out. Will that have an effect on the equilibrium concentration after some time again? If you change the temperature of this reaction at equilibrium, will the equilibrium be shifted to the right or to the left? Or in other words, will this K be larger or will it be smaller? If you change the pressure, will it be larger or will it be smaller? So again, these are things that we'll discuss over the next few slides. Those are concepts, and equally important, you'll be given reactions to apply these concepts and see. So let us start our discussion. So looking at this reaction, so we have acetic acid, look at this reaction right here. So we have acetic acid mixing with ethanol, and this is our catalyst. So it produces here another product called ethyl acetate and water. So we have reactant A, reactant B to give product C and product D. It's a balanced equation, so here's 1, 1, 1. So we need not worry about the coefficients. What Le Chatelier observed is that if you add more acetic acid after this reaction has reached equilibrium, the equilibrium will shift to produce more product. So by adding acetic acid, we have disturbed the original equilibrium, and it moves to produce more ethyl acetate right here and water. The concentration will increase. So it will establish a new equilibrium with a larger equilibrium constant to show that the concentrations are now more in the products than the reactants. If we should do the reverse, it will go in the opposite direction. Okay? Let us look at what happens. So a summary here. So a new equilibrium is established if we should increase the concentration of reactant. So the concentration of ethyl acetate and water is now higher because we increase the concentration of acetic acid. The concentration of acetic acid would be higher because we increased it. But at equilibrium, it will establish a consistent value. So in other words, we say that we have brought about a stress on the equilibrium by adding more of one reactant here, acetic acid, and the equilibrium here has shifted to accommodate that stress, has shifted to accommodate or minimize the stress. The stress here is an increase in concentration of reactant. Let us look at the opposite. If you should remove a product, so here again we have the same reaction and it is at equilibrium. If you should go into this reaction after it has established equilibrium and literally take out some of the product, take it out, what happens? The equilibrium shifts to the right to produce more. So the equilibrium will shift to the right to produce more ethyl acetate, to restore that equilibrium. Okay, so once again you can see this is done a lot in chemistry. If you want a lot of one product, or you can just shift the equilibrium to produce a lot of that product depending on which product you want. Okay, let us look at a practical example here. So when rain falls, it's really water mixed in with sulfuric acid. So rain is typically acidic because of all the sulfur pollution in the air, and it produces some acidity to it. So this is a reaction. So we have here calcium carbonate, a stone, and we have rain coming down which has some sulfuric acid in it. So here's a reaction. Sulfuric acid reacts with calcium carbonate to produce calcium sulfate and carbon dioxide and water. So the question now becomes, if we should, the fact that carbon dioxide is a gas that's coming off. So here's carbon dioxide. So that's a gas, of course, as you know. It will come off as a gas. So this is constantly being lost. Constantly being lost during a rainfall, because gas are very volatile and it will be released. So this is being taken off. So once this equilibrium here has been established, if carbon dioxide is removed, the equilibrium will shift to the right to accommodate producing more carbon dioxide. If that happens, we'll have more erosion of our stone. Right? So this is the conclusion, is that carbon dioxide diffuses from the reaction and equilibrium is shifted, and it shifts to the right and continues to erode the marble or the stone. So that's a practical example of Le Chatelier's observation, known as Le Chatelier's principle. Here's another aspect. If you have an equilibrium, a reaction at equilibrium, and you should change the temperature, heat it up or lower the temperature, what happens? So here is a reaction. So hydrogen plus oxygen is water. Of course, we know that. You mix hydrogen and oxygen, put a catalyst like a spark, you get water. Equally important though, it produces a lot of heat. 137,000 calories per mole of water produced. So for each mole of water that is produced, it produces also 137,000 calories of heat, a lot of heat. So this reaction here is described as exothermic because it produces heat. Exo, remember exo means given off, and thermic here means heat, so it's an exothermic reaction to produce heat. So what is the effect of changing the temperature? If you should increase the temperature here, since this heat here is a part of the product, or can be considered a part of the product, the reaction will shift to the left. So by adding heat increasing the temperature, adding heat, which means increasing the temperature, it pushes the reaction to the left. As you can imagine, removing heat, lower temperature, will cause the reaction will go to the right. So once again, you need to get a good concept or visual of this. So it's the same aspect here, reactants to give products, but here we are including heat as a product. So if you increase this product, the reaction will shift to your left. We can increase this by adding heat, or if you decrease the temperature, take away the heat, the reaction will proceed to the right. We call this an exothermic reaction. As you can imagine, the endothermic reaction is the opposite. So for the endothermic reaction, remember here an endothermic reaction means adding heat to the reaction to get it going. It does not produce heat. You have to add heat to it, adding to the reaction. An increase in temperature will of course drive it to the right. So you can imagine adding heat as part of the reactant. So once you increase the reactant by heat, it will drive it to the right. Of course, the opposite will occur. If you decrease it, it will drive it to the left because you're removing heat from the reactant side, and it will drive that reaction to the left. So the last one that we look at here is that Le Chatelier observed is the effect of changing the pressure. So here is a reaction that we'll examine. But what Le Chatelier observed is that an increase in pressure shifts the reaction towards the side with fewer moles. Notice this is all taking place in the gaseous phase. The fewer moles. Increase in pressure tends to squeeze the molecules together to produce fewer molecules. A decrease in pressure drives the reaction to produce more moles. So again, you may want to pause the video here to absorb this concept. So let us look at this reaction. So notice we have 1 mole of reactant and 2 moles of product. Key, 1 mole and 2 moles of product. So if we increase the pressure based on what Le Chatelier observed is that it will go towards fewer molecules. So here's 1 and here's 2. So if you increase the pressure, it should go over here. If you should decrease the pressure, it should go in this direction for decrease in pressure. So make sure you understand that concept, because now we're going to apply that concept here. So once again, just a review. Make sure you have a balanced equation. Here are the coefficients. And what Le Chatelier observed is that an increase in pressure shifts the equilibrium towards fewer moles of gas. Let us apply that. So if the pressure of the following reaction were increased, select the correct statement. Notice here, increased. I'm underlining increased here. So let's reflect on what Le Chatelier said. If you increase the pressure, it goes towards fewer molecules. So if you should increase the pressure, you would expect it to go in this direction. But the possible choices here are not given in terms of this reactant molecules or product molecules. It is known that this reactant here, dinitrogen tetroxide, is colorless. And the product here is nitrogen dioxide is brown. So if you increase the pressure, it's going towards this direction. Will it become a darker brown or a lighter brown? Because this reactant is colorless. So again, pause the video and think this one through carefully, because the answer is on the next slide. So once again, increase the pressure causes the reaction to shift towards less molecules, fewer molecules. We have 2 molecules of product and only 1 molecule of reactant, so it should shift in this direction. This reactant molecule is colorless, so would you expect it to be darker in color, lighter in color, no change in color, and the equilibrium shifts to the right, or equilibrium shifts to the right? Let's see what's the answer. So here it shifts to a lighter brown, because if you have a dark brown N2O at equilibrium, you increase the pressure, you'll have less of this and more of this, which is colorless, so the color should decrease and get to a lighter color. So therefore, that's how you can tell that the equilibrium was shifted. This is the end of chapter 7. So once again, you will have a quiz on Thursday over which emphasizes the last part of chapter 7. I'll say more in communication to you later on, but it will be multiple choice questions, and of course I think I have about 3 questions where you have to do some calculations, so make sure you have your calculator. So once again, read through the chapter, look at the video, the PowerPoints will be available. Make sure you take your time to make some notes and come up with some examples, solve some problems, and you should be okay. So continue to study hard and get ready for that quiz on Thursday. We're almost there, folks, so keep working hard. Okay? Bye.